And there you are, Jack.
Good. Thanks, Grant. For those sitting at the back, I know my voice does not project very well, and there's not a microphone here, so if you're having trouble hearing, I apologise for that, and maybe you may need to move forward. So I'll start by saying in the 1990s, I was involved with a couple of innovations at the same time at Mount Isa. And I'll use those just to give a bit of a feeling for how innovation can happen and what it takes to cross the valley of death. Because both innovations were very successful. In fact, we developed them at the stage, we applied them, they were really successful at Mount Isa. One of them then went on to become quite successful on the world stage, and the other one didn't disappear, but it never really reached its full potential. It didn't do what we thought it would back in the 1990s. It was a bit disappointing. So I tried to understand what were the features of those two innovations that caused that, to explain what it is that makes some technologies take off and others not really meet their potential. So I broke it down into its components, and you can see that the first innovation, when you look at it, there's some features there that make it difficult. A concept was brought from an unrelated industry. We tried to bring it into mining. It was a very large scale up from its first application. It had to go from batch scale to a continuous processing in mining. Conventional theory said it actually never worked, and we had some enthusiasts who said, well, we don't believe that, we think it can. Needed some complex piloting, a lot of capital to go through that piloting stage. It was going to increase the operating cost and the complexity of the plant. No pre-existing site to refer to, no supplier skills in the field. But if it worked, it would add value. The other innovation was much easier. It had concepts and the reference sites in mining, didn't need new equipment. We understood the theory, didn't need any capital, any piloting. It was going to reduce the operating costs, in fact simplify operations rather than make them more complex, and use the skill sets already had on site. And like the other innovation, if it worked, it was going to add significant value. So I think you can see it's pretty obvious which one succeeded and which one didn't, or sorry, which one didn't take off. There's the first one that took off. Now, that might not be what we all think to start with. And I'll explain those two innovations. The first one, the one that came from manufacturing, small scale paint or chocolate grinding into zinc grinding, was the Isa mill. The second one was mine to mill. Now, the way we applied it at Mount Isa was more, I guess, geomet. It was matching mineralogy and mining, design, plant schedules with ore types and metallurgy. But at the same time was being applied on a lot of other sites for mill throughput. Now, this is a bit of an overreach, I know. Mine to mill didn't die, it has been successful, it continued. And it's something that Water Valeri keeps reminding me that a lot of sites continued with mine to mill. But I guess my point was, but it didn't at Mount Isa. After a few years it was forgotten, it was lost. Some of the other sites, the poster sites that adopted it, let it go. Highland Valley were one, they're rediscovering it now. Other sites did discover it. But the thing is, really, it was free money. It was saying you don't have to spend anything on your site, or very little, and you can make more money. You would have thought that everyone would have taken up free money. So yes, some people did. They kept the flame burning, the candle was still there, and now it is taking off again. The interesting thing is, though, why wasn't it adopted much more widely during the 1990s and 2000s? And so I use these two examples to highlight two of the points I'm going to conclude with at the end. First of all, for an innovation to really take root, the operators desperately need it. Now, in the early 1990s, we desperately needed both of these at Mount Isa because we're going to go out of business. The ore was getting finer grained. We had to grind finer. We needed something. But that still wasn't enough. We had difficult ore and we had to integrate mining operations with processing to survive. The mining boom didn't change the grain size, so we still needed the isomil, but it changed the need to survive by mine to mill. And so that is why I think most operations dropped it. They didn't need it to survive anymore. They were making lots of money. And there was innovation that sort of broke one of the other rules. If possible, when you develop an innovation, try not to cross organisational barriers, because that greatly increases the complexity, or organisational boundaries. Or if you do, then you have to make sure you change the organisational systems to suit the innovation. So, the innovation valley of death. I'm sure everyone has seen the typical technology adoption curve drawn as an S-shaped curve. In fact, it isn't quite S-shaped. Well, it is, but there's a discontinuity somewhere around here. After the early enthusiasts, and the first inventor and the early enthusiasts adopted, there's a discontinuity where it isn't sure whether that technology will follow this path, to widespread adoption, or if it will maybe not die, but just become a curiosity, a niche technology at a couple of sites, gradually fading away. And the simple way I use to explain this curve is on this side of this continuity, the people at most companies are worried, if I buy this technology, I might get sacked if it doesn't work. On this side of the curve, they're saying, if I don't buy this technology, I might get sacked. So how do we get across that valley of death? Well, actually, it isn't as simple as that, because before you even get to that valley of death, you've got to get across the hidden valley, which is getting from the first concept of the technology to your first installation. So that adoption curve you saw is after the first commercial installation, the first successful installation. Then you're ready to go across the valley of death. So, I don't know, does anyone have any feelings that, how long do you think it takes to get through either one of those or both of those valleys? 5 years? Each, or?
Well, I always think of 10 years as being the minimum to go from your idea to start to pay your money back.
Yeah, okay. So Philip, so 10 years from concept to pay your money back. So we'll come back to that. So I'm going to go through a couple of the technologies, or just a couple of examples from my experience. So the iron smelt technology, and some of you may have seen a presentation by Chris Fountain here last year, I think, which had some of this detail in. Now, this, to be fair, iron smelt is a very complex technology. It's not a single bit of gear, it's a whole smelting technology. So it's more complex than the majority. But that started the concept. Well, I'm not sure when John Floyd first thought of it, but the lance was really demonstrated in 1973. And then we went through a series of smelting tests for Mount Isa, bench scale tests, and then a stage, or series of the pilot plant tests to demonstrate in the operation, until about 20 years later, after the concept, the first full-scale installation at Mount Isa, or large-scale commercial production plant. And indeed, that, although Isafelt's complex and it was a 20-year journey across the Hidden Valley, but the path was common. Starting with the concept and the theory, you need some sort of proof at the bench scale. And then the path we took at Mount Isa, and I really think it's not the only path that's close to it. You have to demonstrate it in your plant, or in a plant, the one that's going to adopt it. As we know, scale up is difficult. You can't go from a small scale to large scale in one step. You need several steps. And that costs a lot of money. That needs a lot of funding. And so the logic that we applied was that's only going to happen if each scale-up step is embedded in production, and that the operators, the maintenance people, the engineers, the researchers, the technologists are forced, absolutely have to work together to make it work. And each of those plants become a part of the production, a part of the production budget, so it has to work. And if it does work, it pays its capital back and it justifies the next stage of scale-up. So each stage was designed so that the 5 tonne an hour, okay, if it works, it's going to make this much extra lead per year, that will pay back for the plant. And when it's running, we now know how to build the 10 tonne per hour plant. And when that's running, then we know how to build the 20 tonne per hour plant. And at each stage, we solve the scale-up problem progressively. But that takes millions of dollars of capital. But it's staged, because you only risk it at each point. You only risk the next stage. If it doesn't work in the plant, if you can't make your budget, you've only lost that stage, not the full step. And that gets you to the first commercial stage installation. As I said, in the case of Isosmelt, it was about 20 years. For the other technologies, Isomill was a lot less than that, because it's not a whole plant operation. It's almost a point solution within the plant. But that's not the end of it, because once you've built that plant, that's when you find your final level of problems, of issues. Things that may not be, or probably aren't, visible at the small scale, or at the intermediate scales, but when you're in full-scale production and your whole production relies on it, that's when you really find out about the little niggling operating issues, the niggling maintenance issues that really will determine whether this technology is going to be successful. And that's when you solve those fine details. So really, even at this stage, you still only have the beta model. And you can rush to market faster than that if you want. And you might like to ask Samsung how that worked for them, their latest phone. So depending on the technology, for Isosmelt, it's a 20-year journey. For others, I'd say it's maybe 5 if it's relatively simple, but somewhere between 5 and 10 to get through each of those stages. So after all that work, we cross the Hidden Valley, and that's when it really gets hard. Because now, the people we're trying to market to, they're not our own company. They're not enthusiasts about their technology. They're not in love with their technology. They just want to do something for their plant. They don't care about how elegant it is. They say, what does it do for me? And then you're starting to deal with competitors who have a vested interest in it failing. And they play hard. They really want it to fail, and they'll do their best to help it fail, and they'll spread any little bit of information or misinformation they can to try to make sure it doesn't cross that valley of death, because that hurts them if it does. So, I'm not sure if any of you have read this book, but I strongly recommend it. A lot of people talk about disruptive technologies, and perhaps Christensen wasn't the first person to use that term, but he explains it very well, and explains how technologies can disrupt an entire industry, and how very well-established companies can lose their business because they didn't see a threat coming from a new technology that did cross the valley of death and caught them by surprise. It's an excellent book, but the one thing, it doesn't help us that much here, because it's in hindsight, it looks at those technologies that did cross the valley of death. It doesn't predict which ones are going to cross that valley. So, to be successful, every technology has to have some disruptive elements. It has to be better than what's there before. It has to be really good. And that's an absolutely necessary condition. Otherwise, it's not going to take off. It's necessary, but it's not a sufficient condition. There's a lot of good technologies that don't make it. So there's a lot of other things have to happen as well as being disruptive. to get across the valley. So I just tell some stories, and actually probably Philip would be able to tell some of these stories because he personally experienced it. But the Jameson cell had a similar development, scale up from concept, different stages of plant evolution, plant demonstration. And, we thought we did everything right. We had a really good installation in lead zinc concentrator that worked very well. In hindsight, MIM went to market a little bit too early because the installation we had worked really well, but it turned out it was within a high circulating load and had a very steady feed. And the plant, or the cell at that stage, hadn't really been developed as far as we needed to. It was like a sports car that was very good on a flat road, but it wasn't good for crossing a riverbed, which is what operations are. And so when it got to some more difficult operations, those flaws showed up for the first time. And so we were MIM, sold some early cells to Keep Creek in Canada and installed them in Alabama. And there's nothing wrong with them, they just weren't robust enough yet for that application. We hadn't learned how to make them deal with varying feed. And we hadn't learned how to integrate them properly with, or in the best way with conventional cells. We sort of thought these are better than cells, so they're the solution. And in fact, almost every technology by itself is not the solution. It has to be integrated with other technologies, and that will determine how it works, how it integrates with the rest of the plant. And we hadn't really solved that. And so those two installations were, they worked, but they weren't great successes. As a result of which, we never sold another Jameson cell in base metals for 10 years. We have never ever sold one in Argentina or Chile since, 20 years later. The reputation's got around, helped by our competitors, helped by everyone in the industry. And about 10 years ago, we said we're going to crack the base metals market again. We had one bit of luck here, and Philip was a part of this, well, luck and good management, that we were able to do all the development work in coal. The bit of luck is that what we thought, I used to think was a disadvantage, coal people don't talk to base metals people. They don't like it. I thought that was bad. This is the time it turned out to be good because the coal people were happy with what the cell did for them, and that gave us a chance to develop it and to make it robust and then make the relaunch back into base metals. But we lost 10 years in the wilderness. Similar story on isosmelt, and again this is from Chris Fountain's presentation, but it wasn't until we got to full scale that we really understood the refractory life issues. From the pilot plant work, it didn't show up. Even at the next, or the size below, before the final scale up to full size, we're getting 2 years life, 2 years refractory life. That was okay. But for the first 7 campaigns in isosmelt, we were averaged about a year life. Now, a shutdown of a smelter is a real pain. You lose production for about a month. It's a major job. You've got a high cost, take out all the old bricks, put new bricks in, cool the furnace down, reheat it. It's a major disruption. And frankly, 1 year refractory life is not a viable product. It was still good technology. It just wasn't good enough. And it took us 7 years to learn all the little tricks about temperature control and lance control and brick type and slag type. I mean, a whole lot of tricks had to be put together to work out, if we put all that together, we can get 3 or 4 year refractory life. And I don't know how we would have done that in less than 7 years, which is what it took. And I guess a bit of luck here again, we hadn't sold too many smelters in that 7 years, so we didn't get such a bad reputation. By the time the technology was really taken up, we had the solution for long refractory life from our own operations. And so the isosmelt adoption, this is the first plant at Mount Isa. From there, I guess you could say the valley of death is somewhere around here, so somewhere around 12 to 13 years, where we can safely say we're there now. People are buying this, they're referring it. We're happy to send people to some of the overseas installations to get references. So in that case, 20 years development from concept, and then another 13 years over the innovation valley of death. In the case of Ironman, from concept to the first commercial scale was a bit faster. As I said, it's a relatively simpler technology. A pile plant mill is not that big. It can be stored at a part of the plant, not the whole plant. But again, the first large-scale installation in 94, it's somewhere around here, probably 2007, 2008, you could say, we're over that valley of death. And bear in mind, these first installations were largely internal, so we didn't have to convince external customers, we didn't have to fight off competitors. These people were enthusiasts and they knew what they needed. So it was somewhere around here, again, 12, 15 years. Now, Soro and others have done studies and they say typically that's about the time from the first commercial demonstration of technology in the mining industry until it's widely accepted is somewhere between 15 to 20 years. So we did a little bit better than that, but not much. And so people often say, well, that's because the mining industry is really conservative, too conservative. Actually, I don't think that's the right solution. When I hear suppliers say that, I mean, it does make us feel better over a glass of wine at night and we have a whinge and a complaint about it, but I think actually that underestimates the difficulty and the complexity of the industry. Operations are highly complex, interrelated beasts. All these moving parts are connected. You make one change somewhere else, somewhere it has another change, somewhere you never even anticipated, somewhere else in the operation. And so the trouble is, if you're selling a point solution, rarely does a point solution work. And that's what I said about the first gems and cells. If we didn't understand how it interacts with the other flotation cells, then we don't have a full solution yet. We've got a point solution, but the sites need an integrated solution, not a point solution. So again, when I say people say the mining industry is conservative, I think, well, maybe you don't understand their business enough, because I don't think they're conservative at all. I think the mining industry is bold. And so it has a right to be cautious about what it does. When you look at a mining operation, what maybe nowadays $5 billion investment in a country where you're not sure what the government's going to be in 10 years' time when you start up, you're not sure what the environmental legislation is going to be, you're not even really sure whether your product is, in 10 years' time is still going to be environmentally favoured or disfavoured. You can't move the asset. The only possible application is on that ore body where you've just sunk the money. And on top of all that, even with, now Alice maybe want to comment on this, but even with the best drilling program in the world, you've actually only sampled about 0.001% of the ore body. So you really, sorry Alice, you really don't know exactly what's there or exactly how the ore body is faulted or developed until you get there.
So you have this.
And so on top of all that, you then ask the board to take a technical risk as well. I just think that's saying, God, we're taking enough risk, and we know if we put 1 foot wrong, yeah, Murrin, Causey, Ravensthorpe, HBI, any number of failures where people put a technical foot wrong. So it's not fair to ask them to take risk. You have to remove risk for them. So I think that's really the job of the technology commercialiser, is to say, how can I make this technology, how can I implement it in a way that demonstrates to the site that their risk is lowered, not increased. Now, we talked before about disruptive technology. Does anyone think that a vibrating screen is disruptive technology. So, as you know, I work with CRC Ore, and we've worked at a number of sites where either a relatively simple screening step of the plant feed, or maybe the mill scats, or selective blasting and then screening of the product could significantly upgrade the mill feed. So in one case, just taking the mill feed and screening it, removing the oversize, would put 88% of the metal value into 30% of the weight. Now that sounds like a hell of a deal to me. But as soon as you present that to the sites, they say, well, or the production manager, you say, well, what? I've just got the ore from a loader into a truck, and it's on its way to the mill. Now you want me to tip it out of the truck, put it on the pile, pick it up with another loader, put it on the conveyor, feed a screen, now make 2 piles. So I need another 2 loaders to pick up 1 pile and put it in another truck back to the mill, and another loader, put another truck to a stockpile, which I don't have yet, by the way. And then I don't have the trucks, and I don't have the loaders, and I don't even have anywhere to put that conveyor you're talking about, or the stockpile. And anyway, if I do that, now the mill's sucking air, and it's got 70% less feed, and I'm going to get my ass kicked because the mill's not full. That is a highly disruptive unit process for that person. Now, if you thought about it at the very start of the mine, it's not disruptive design around it. But once the mine is in operation, it's almost an insurmountable problem to put in a screen. So that's why we have to understand, so what is it that drives operators day to day? How do they get through their job day to day, and how do we help them? So a couple of things that I guess really only dawned on me later in life is that, I mean, we always say the mining industry is a small industry. It really is a small industry compared with manufacturing. So, because someone pointed out to me, in the manufacturing industry, people say mining should be like manufacturing, and I think that misses the point. Yes, we know that. We've known that for 50 years. We should be more like manufacturing. But there are real reasons why mining is different. One of them is that every ore body is different, and it is relatively small, and there are no major system integrators that are happy to go to a site and say, look, we have a solution, we can apply that here, buy our solution for your factory, and this will work. We just program it for you. And even if there were, as someone said, they've probably only got 5 customers in the world, unlike manufacturing. So the KPMGs or Pricewaterhouses don't develop those sort of large-scale integrated solutions for mining because there's only a couple of customers. And point solutions aren't enough. And I've given some examples of that you have to consider the whole system context. How does it affect everything in the system? How does it affect the tailings, the water quality, the upstream equipment, the downstream equipment, the circulating loads? If you don't understand that, it might look as though it's going to work, but it won't work properly or well when it goes into the plant. As you said, the business is already too risky, so don't add risk, remove risk. And I do believe the only way to do that is it has to be demonstrated in someone's own plant. That also gives you the chance to show how it interacts with their own equipment. So when people say, you know, we'll demonstrate it at the pilot plant or we'll demonstrate it somewhere else, another plant, that won't get you very far at all. You have to, I believe almost every time, you have to show someone in their site how that's going to work for them, how it works in their unique situation. Even simple changes are disruptive, like the screen. So that means you have to look for things that are necessary for the site. Yeah, people are really busy. They've got so many priorities. They really only have, well, in fact, they don't have time to do any more work. If there's more work to be done, it's going to be done out of hours and on the weekend. And they're only going to do that if it's really necessary. And if possible, it's much, much easier if you can make those installations incremental to production rather than part of the whole production stream. So as soon as you put someone's entire production stream at threat, like a screen, interrupting the feed to put over a screen, that's interrupting the whole production flow. If you could do that on a small scale screen, if that site happened to have 5 production lines and you're able to do it on one of them, you've got a chance. And in the end, how hard it is to maintain and how hard it is to operate will always win. If you put it in a couple of sites and it's just a maintenance nightmare, if it's just a maintenance nightmare or an operating nightmare, people won't like it and they won't give it good references. And people's KPIs will also win too. Now that's why I believe Mine to Mill didn't, in those days, cross the valley of death, because in the end, blasting engineers' KPIs and the mining engineers' KPIs and the metallurgist's KPIs were not aligned for Mine to Mill. In spite of the KPIs, we made it work, but as soon as it was no longer necessary, it shrunk back to what it had been before. So if you can, avoid crossing organisational boundaries. It's not always possible. But whatever you do, try to make someone's job easier, not harder. It's already too hard. They just want someone to help them get through their day and meet their targets. And if you can, find a way to make people win. Make it their idea, give them the credit for it, find out what it is that motivates them or that has to get them through their day, and try to make them successful. So, go back to the Isomel example. I said that took about 13 years to cross the valley of death. And when I think about it, we had a following wind. We had a lot of help. To start with, we had a critical mass of technology people, and we had a supportive management over a decade or so that was allowed us to research, invest in the technology, demonstrate at the plant. We had some large-scale early users at Isa and Carpet River. Those sites, because they're internal users, were able to take risks there. We were able to demonstrate equipment, wear parts, improve designs. We had an established high-quality manufacturer in Nets. They've been in the fine grinding business for about 50 to 100 years before we even developed the Isomel. Our company let us market it, and that's quite unusual. Most companies, BHPs, Rios, would not allow internal technology to be marketed, let alone support it and welcome visitors to the site. We had a compelling case history at Mount Isa. If anyone saw Tim Napier-Munn's talk the other week, how we had a plot of the mineralogy over the years, the decline, what happened when we did different steps, including the Isomel. We had a marketing team that had all come out of the technology. They understood it. They understood how to apply it. The first installations, or our installations, were in flotation, but coincidentally we discovered an application in leaching, and that got us some of the early external applications where we didn't need to convince people that fines float. Large portions of the minerals industry still believe you can't float fines, in spite of all the evidence to the contrary. Leaching people, you don't have to convince them that. They don't want them to float, they just want to dissolve them. At that time, it was the right technology for the right time. Ores are getting finer grained and needed finer grinding. And finally, to really put the cream on the cake, we were marketing it in a once-in-a-lifetime commodities boom. We had great timing. So, with all that, it still took us about 13 years to get across the valley of death. I hear people now say, "Oh, well, if we just worked harder, if we just work like manufacturing, we cross it in 5 years." Now, I'm not talking for software or services. I'm talking equipment, major equipment changes. So I think Daryl Hannigan would have the answer better than I would. Honestly, you're dreaming. Okay, to sum everything up, from my experience, I've thought of 7 necessary conditions to successfully innovate. I said the driving need. People are too busy. The older saying, necessity is the mother of invention. It absolutely has to be necessary. If it's just an improvement, it's not good enough. People don't have time to do it. It's got to be designed for your all. No one cares. And that was one of the mistakes we made early on. We told people about these wonderful things we did at Mount Isa, really thinking they care. They don't care. They want to know, they don't care what it did for us. They want to know what's it going to do for me. And the only way to do that is to do the work on their all in their plan. Obviously, you need passionate champions. The bite-sized implementation, so that goes back to the screen example. Don't try to disrupt, if you can, don't disrupt the whole feed. Take a small portion of the feed out, or find a stream where you can apply it, demonstrate it without disrupting production. As soon as you disrupt production, you're in a whole new world of pain in terms of getting approval. Simple IP rights. It's okay for the company to want to get their money back. So we've invested in R&D, we should be able to license to other companies. But geez, don't make it hard. Do not make it hard for the company adopting it or the company marketing it to make some money or to adopt the technology. And in the minerals business, you need high quality ongoing support. So one of the main things we did in Extractor Technology, I think successful things, was that we had people who would go to site to demonstrate it, and we had people who go to site to commission it and to support afterwards, because everyone just wants to work in their site. They don't care about anywhere else. That it has to work for me. If you've got the experts, you have to give them the experts to make it work. And then you need enabling organisation systems. So that's where I said, aligning the KPIs. You can't always do that in other companies. Well, in fact, you can't do it at all. But you have to really try to design your gear or design the implementation around how is this going to work with the company's KPIs in their organisational systems. Now, I said there were 7. Actually, I lied. I can't keep 8 things in my mind at once, but there's one more condition. That's timing and luck. Now, the non-Australians probably don't recognise Stuart McGill was one of the greatest leg spin bowlers in Australia, but he had really crap luck timing. You know what it was? He was born at the same time as Shane Warne. He was never going to play for Australia as much as Shane Warne did. And that's in sport and in life. There's an awful lot. You can do everything else right. You still got to be in the right place at the right time. The Jameson cell, we were lucky that coal didn't talk to base metals, and we had another chance to develop it. In the Isa smelt, we were lucky that we didn't sell many early on. Those early failures weren't fatal because we were able to sort out the refractory life internally before it went external and someone trashed their reputation forever. But had someone, at the time we would have thought it'd been good if someone had bought another Isa smelt in 1995, it would have been fatal if they had to the technology. So, they're the 8 platforms. I believe you have to align. All these things have to happen. You miss one of them, it's really going to be hard to cross that valley of death. Thank you.